Welcome back to chapter 16. We are continuing with our discussion about waves and resonance. And now I want to talk about standing waves. So a standing wave is a result when you have constructive and destructive interference. And it occurs when two waves have the same frequency, but they meet traveling in opposite directions. You can do this if two people hold a rope and they shake opposite ends at just the right frequency. If you have a car that has a wire antenna that sticks up, sometimes as you travel down the highway, it'll set up standing waves. And we're going to do it in lab. We will be able to shake a string and generate standing waves. So with a standing wave, even though the string or the wire or whatever it is looks stationary, that's why they call it a standing wave. It looks like it's standing still. Even though it looks stationary, it's really moving. And like I said, it just moves in concert and very quickly. And we'll do this in lab. So with a standing wave, we have nodes and antinodes. Nodes are points of destructive interference, so they don't move. They're stationary on the wave axis. Antinodes are points of constructive interference, so they have maximum displacement. So in this first drawing, an antinode is the high point. So this is an antinode, and we have nodes at either end. In the second drawing, you have two antinodes and 1, 2, 3 nodes. And then we have a last diagram where we have excuse me, 3 antinodes and 1, 2, 3, 4 nodes. So with all of these, the rope is the same length. It's just how we're shaking it. Oh dear, I'm gonna have to plug in. I can do this. Sorry about the interruption. All right, so we get back to physics. So for the first one, it's referred to as the fundamental frequency or the first harmonic. The fundamental frequency or the first harmonic. The number on the harmonic corresponds to the number of antinodes or the number of loops, whichever way you want to think of it. If we look at our second picture, it has 2 loops, so it's the second harmonic. The third picture has 3 loops, so it's the third harmonic. With this, the number of loops harmonizes or matches up with the number on the harmonics. The fundamental frequency is what we start out with, 1 loop. The first overtone, you'll notice that tells us we've got 1 loop over the fundamental. So if the fundamental had 1, the first overtone is going to have 1, 2. So 1 more than the fundamental. This one has 2 more than the fundamental, so it's the second overtone. All right, it's important to understand the naming system we use. If the length of the string is L, and little n is the number of antinodes you have, or loops, so 1 loop, 2 loops, 3 loops, then the relationship between the length of the string and the number of loops we see and the wavelength will be that L equals, for the first one, where n is 1, L is going to equal 1 times lambda sub 1 divided by 2. So it's a half a wavelength. Remember, a wave, you come up and you go down. So this is half of that, half a wavelength. This is a whole wavelength. So L is equal to lambda sub 2, but if we write it as some number over 2, it'd be 2 lambda sub 2 over 2. This one is 1.5, so 3 halves. L equals 3 lambda sub 3 over 2. 3 lambda sub 3 over 2. Why am I doing this? Well, we want to write an equation, and the way to do that is to see what your pattern is. So our pattern, oh, I'm sorry, we've got a photograph. So this is a fluorescent string set up to a vibrating device. And you can see we have the fundamental or the first harmonic, This is the second harmonic or the first overtone. This is what? The 1, 2, 3, fourth harmonic or the third overtone. And that last one's got so many I don't even want to count it. Alrighty, so in general, L is equal to N times lambda sub N over 2. L equals N lambda over 2. Or if we want to rearrange it, we could say that lambda sub N is equal to 2L over N. Lambda is going to be 2L over N. So to find the frequency, you could remember that V equals lambda F. Velocity equals wavelength times frequency. We could rearrange. And then we could add little subscript n's because each of those little pictures had different wavelengths. But we know that lambda is 2L over N, so we could plug all that in and we get that the frequency is N times V over 2L. Frequency is going to be N times V over 2L. Remember, N is the number of loops or the number on the harmonic, V is the velocity, and L is the length. Now, something you may not know is that the frequency for the second harmonic is 2 times the frequency for the first harmonic. The frequency for the third harmonic is 3 times the frequency for the first, and so on. So we could say that F sub N is equal to N times F1. Let's do some examples. I think this is confusing in the best of times, and the examples will be helpful. So we want to know what is the frequency of the sixth harmonic. So sixth harmonic means N equals 6. For a string with a fundamental frequency of 500 hertz. Fundamental frequency is F1. So F1 is 500 hertz, N is 6. We want to find F6. Well, the two formulas you need to know for these sorts of problems are that Fn is N multiplied by F1, and Fn is N times V divided by 2L. So we don't have any L's or V's. We can't use the second equation, but we can use the first one. So Fn is N times F1. We are looking for F6. So F6 is going to be 6 times F1. So 6 times 500, which gives us 3,000 hertz. Frequency is measured in hertz. Let's do another example. What's the fundamental frequency if the third overtone is 4,000 hertz? Third overtone, N would be 3 plus 1 or 4. So F sub 4 is 4,000 hertz. And they want us to find F1. So again, we use Fn is equal to N times F1. We know F4, it's 4,000. So that means N is 4 and F1 is what we're trying to solve for. And that means that F1 is 1,000 hertz. Now we'll get even trickier. What's the third overtone if the sixth harmonic is 3,600 hertz? Third overtone if we know that the sixth harmonic is 3,600 hertz. So what do we know? We know that third overtone means N is going to be 1 plus 3 or 4. So we're trying to find F4. We've got the sixth harmonic. Sixth harmonic tells us that N is equal to 6. And we know that F6 is equal to 3,600 hertz. The formula we need is Fn is equal to N times F1. And we can use that to find the fundamental, F1. So F6 will be 6 times F1, 3,600 hertz will be 6 times F1, divide by 6. We know the fundamental is 600 hertz. If you know the fundamental, you know every harmonic and every overtone. So once we know that the fundamental is 600 hertz, we can find F4 because it's going to be 4 times that. So F4 will be 4 times F1. 4 times 600 hertz is 2,400 hertz. All right, let's do something a little more challenging. And that is, we want to talk about changing the length of the string to change the frequency. So suppose we have a 4-meter long string. We're making, that's over 12 feet. That's actually, it's over 13 feet. So it's really long. We're making a really big guitar. So we know that L is 4 meters. It has a fundamental frequency of 2000 hertz. So F1 is 2000 hertz. We want to fret down 1/4 of the way. What does that mean? Fretting down is when you press down on a string and only strum then part of it. When you play a guitar, when you press on the strings, you are fretting. And so you're effectively shortening them. It's a way to make the strings shorter without physically cutting them. In a piano, you have lots of strings and there are lots of thicknesses and lengths. But on a guitar, you have 6 strings. And you have to press down on them to get different combinations. So that's called fretting down. So if you fret down 1/4 of the way, that means you're only using 3/4 of the string. So your new length will be 3/4 times the original length. Our original length was 4 meters. So 4 meters times 3/4 is 3 meters. If we'd fretted down halfway, we'd only be using half the string. It would be 2 meters. If we'd fretted down 10 centimeters, you'd be using 3.9 meters worth of string. So you ought to be able to figure out, if I tell you how far you fret down, either by giving you an amount or a fraction, you ought to be able to tell me how much is left over. And if you struggle with that, let me know and I'll give you practice problems. So they said, what's the new fundamental frequency? So F1 new, that's what we're looking for. And we know that Fn is n times F1. Well, we've only got fundamentals, so that was not going to be very useful. But we also know that Fn is n times V divided by 2L. So we know a fundamental frequency, we know an original length, we can find the velocity. So Fn is equal to n times V divided by 2L. So 2000 hertz is 1 times V divided by 2 times 4 meters. Now that means that V is going to be 8 meters times 2000 hertz, or 16,000 meters per second. Now the thing about the velocity is that when you fret down, the velocity does not change. The velocity depends on what the wire is made out of. Is it a nylon string on our really big guitar, or is it made out of metal? And its diameter, but we didn't change either one of those. We didn't change what it was made out of or how fat it is. We just changed how long. And changing how long does not change the speed with which the vibration travels through the string. So once you find the velocity, you know it for that string, even if we cut it in half or quarters or 16ths, it doesn't matter. Once you know the velocity, you always know the velocity for that particular type of string. So 16,000 meters per second. Now that we know V and a new L, we can find a new F. So step 2 is to find the new F. F1 new is going to be n times V divided by 2 times the new length. So 1 times 16,000 meters per second divided by 2 times 3 meters. So 16,000 meters per second divided by 6 meters gives us 2,666.7 hertz, because frequency is measured in hertz. Hertz is a cycle per second, and remember, cycles aren't really units, so hertz. And that finishes us. We are done. You need to definitely work on your problems. If you need help, you need to ask me for help.